So here today I'm going to talk about epileptic seizure detection from EEG by time frequency analysis. And I'm Amin Hudamadi, computer science PhD student at University of Sega. So let's get inside of the content here. As you can understand from the title, it's related to a kind of disorder, epileptic seizure, which is a manifest of epilepsy, which can occur on brain structure and cerebral cortex. So we can consider electroencephalogram to record this brain activity or neural activity to distinguish disorder from some manifest, which I'm going to talk a little bit later about it. So first of all, to get to know more about epilepsy, I will mention a little definition. What is exactly epilepsy is? The paper said that about 1% of the population in the world can suffer this neurological disorder, and some of them can do some convulsive medicine, some of them can do some surgery, but the rest of them can't receive any good treatment. So epileptic seizure detection would be very urgent method for some people. But what is the epileptic seizure or epilepsy? Related to some normal brain functions characterized by existence of abnormal synchronized discharges, which discharges can be known as paroxysmal activity, which can be occur in some part of the brain, which known as partial seizures, or can be occur in the whole brain, which known as general seizures. And because these can occur in cerebral cortex, we can record it by EEG or electroencephalogram. Is a device to record the cerebral cortex or neural activity. And if they're occurring partial part of the brain, some of the EEG channels can record those signals. And if it occurs in the whole of brain, the whole channels of the EEG can record it. But the main manifest of the epilepsy is epileptic seizure, but during the epilepsy, or we call it ictal period, or between every ictal period or seizure, we call it interictal periods. Most of the scientists are going to record interictal, about 20 minutes of interictal periods, because there is a very common features between interictal and ictal, and known as spike and wave complexes. But the most important manifest of epilepsy is epileptic seizure. But still, we can distinguish if we could consider interictal period inside of the EEG signals, then we can say that in most probability, persons suffer of epilepsy. So how we can distinguish this interictal manifest of epilepsy inside of the EEG channel, EEG signals? There are some very earlier work like 50 and parametric methods, which they applied to the EEG signals, and they did it with some, they consider some earlier observation of signal rise up suddenly on some frequency band, like you can see here between like 4 and 8 hertz, as it was mentioned in some previous works. But the most problem was about the inheritance of seizure evolutionary, because seizure evolutionary is dynamic, non-stationary, and also multi-component, and they didn't consider the composition of the signal into some basic signals. So the solution comes up or rise up with some TF analysis, which I'm going to tell you a little bit about it. So the related works decompose to two classes for interictal event detection or a spike detection, which did some wavelet transform on EEG or some other recording things, and ANN classifier, IC, and so on. And another group was epileptic seizure analysis, which include detection, prediction, and automatic focus channel identification, which in this paper we're focused on epileptic seizure detection from intellectual event detection. So for doing this, this is the paradigm for this paper. And you can see the whole procedure of, at the end, we can say that if a person classified as a seizure or not seizure. So the first stage is EEG. You can see is the hat put on your head and record the data by some channels. Related how many channels have your EEG had, 128, 64, and so on. And these recorded signals can be recorded here. You can see as different channels, and then extract some features. Here in this paper, they're going to use short-time Fourier transform and compare it with some other methods for feature extraction, and see as a power spectrum density, and see as a spectrogram of this power spectrum density. Then feature extraction applied to decrease the number of features, and then with PCA, and then feed it to a classifier to see if a person suffer from seizure or not seizure. So get to depth, let's do in depth inside of this. So for short-time Fourier transform, for extracting features from the signal, I will let you know a little bit about Fourier transform, because we have to do Fourier transform for do short-time Fourier transform. For Fourier transform, we have a filter bank here. You can see, I don't know if you can see my pointer or not, but in red signal, this red signal is a filter bank signal, which is a unit distance between every peak applied to the whole signals, and then you can extract features like spectrum or energy inside of that signal. Or if you want to understand a little bit more better, I can give you an example. Like when we are talking, the shape of our mouth can produce different vowels or different sounds, but the air go out from our throat or our vocal tract is the same. Just shape will be different and the voice will be different. So these kernels are play a role like a shape of our mouth. Then here you can see wavelets. Wavelet transform is like Fourier transform, but in compare of Fourier, there is just some part of the wavelet with some punctuation. Here you can see if you apply or product this filter on your original signal in some region. For example, if you want this part of your signal, see the energy inside of it, then you have to slide this filter bank, go on this signal, over the signal to arrive here and see the energy in this part of your signal. But I mentioned wavelet because it's related to the short-time Fourier transform. They are doing the same things, but there's a difference. I will let you know a little bit later. Short Fourier transform is actually like wavelet. So there is a small window on some part of your basic signal, and then you can see here, this is the signal extracted from that window, and then apply Fourier transform to that signal to see a spectrum or power or energy inside of this signal. Instead of applying Fourier transform to whole of the signal, you just apply it for a small window of the signal, which known as a short window. Then for receive a spectrogram of this signal, we're going to rotate this chart like frequency axis convert to the y-axis as a frequency, and power of the signal here shows as a color of this frequency, difference frequency. If you have more frequency, it goes like more red, which is more power of the signal. And this is for that time, that specific window time. We have a Fourier transform of that time, that specific time. So in compare of wavelet, the short Fourier transform, there is a big difference here. For the wavelet, you will apply this kernel in the whole signal. So instead of just having one time with lots of frequency in wavelet, you have one frequency over the whole time. Okay, this is the big difference between wavelet and short Fourier transform. So, but there are also some parameters inside of the short Fourier transform we need to consider it. First of all is the window size. And for consider window size, we need to consider a trade-off between two things. Because if our window size rises up, then the precision, temporal precision then go down, but frequency power spectrum goes up, because then the color would be more because the frequency are more. But if our window decreases, then temporal precision goes down, but it goes up, but frequency spectrum goes down, because there are little frequency and not very clear color. Another parameter we need to consider for short time Fourier transform is time sliding the window over the time, like 10 milliseconds we need to slide the window, then we have some overlap for the previous slide over the next slide, how much we need to consider for sliding the window. Another parameter we need to consider is not only the size of the window over the time, even size of the window over the frequency. So these are some parameters we need to consider about the short time Fourier transform. And in this paper, did the short time Fourier transform and compare it with some other kernels, other methods to extract features. And here you can see, for example, WI, the first three methods without any kernel or complex kernel did to that signal to extract features and use it as a classification or some other feature dimensional reduction, and then classification for next step. I will let you know more. So here you can see at the top left side, there is at the first row, you can see the EEG segment, and then you can see the short time Fourier transform spectrogram of that signal, and the rest of them are 12 another methods applied to the signal, and then you can extract feature and do the rest of the steps. So for feature extraction here, they consider three partition over the time with equal size for each segment, and over the frequency 5 partition, which known as this frequency I mentioned here. So there is 5 for each time window. It goes 5, 10, and 15 features, and one features here is the calculated for the whole segment as this formula calculated that value. So we have 16 values for 16 values feature for every segment. Then we need to apply feature dimensional reduction, because then we have a lot of features. For dimensional reduction, PCA applied. And for PCA, consider 1% threshold and 3 or 4 extracted feature result for the whole of the rest of the method. So after that, apply classification with doing classification ANN with hidden layer and the activation function of sigmoid, and for the output, consider linear function. For naive-based classifier, they consider the attributes of each values or differ from attributes of the rest of the values of the other classes for that class as well. For decision tree, they consider that they consider a recursive partitioning algorithm, and when our information gain will be decreased if we divide data to sub-data. And in decision tree, we have nodes, branches, and leaves, which known as variables, condition, and outcome. And for k-nearest neighbor, considers each sample known as unknown sample, and then measure the similarity distance between this unknown sample and the rest of the samples to put it on that class. And for logistic regression classification, they use the linear regression. I will let you know a little bit briefly later. So in this paper, they consider the data set from this website, which used in the previous papers, with 128 EEG channels and 100 EEG segments. So we have 100 EEG segments for each classes. And what are our classes? So we have five class, two class from healthy people, which Z is healthy people with open eyes, and O is healthy people with closed eyes. So we have 100 segments for each of them. And N and F and S are related to the patients. N and F are related to the patients with seizure-free, but S is related to the patient with seizure. So here we have 500 segments for the classification, here 300 and here 200. So for the evaluation, they consider this evaluation of the classification for each of these time frequency distribution. They consider sensitivity and selectivity for each of that classification between different classes. And for cross validation, for get rid of overfitting, they use cross validation with 50 split data, 50 for training and 50 for test, and applied 10 times like ANN to see the result and average for the 10 times, and mention it here. So after that, okay, I will let you know a little bit here. So here you can see two big difference between MH and MH extraction feature from the original signal, which you can see for two classes. Okay. For short-term Fourier transform, for 2 class and 3 class, it's obviously a good result, but for 5 class, it's not very good, as well as other methods except these 2 methods. You can see when the number of classes goes up, then the average value goes down, and there is a note here. I will let you know why. But for 2 methods like MH and RIH, you can see there is not very good average value for precision, and the reason is because this 2 method didn't use actually a smoothing window like MH and RIH, but still WV also didn't use the smoothing window, but receive good result like those use complex kernel, but actually they didn't mention why, and I couldn't understand what was the reason, because WV also didn't use the complex kernel but received very good result here. And if you know it, just let me know. So it was the reason because of the didn't use the kernel, they didn't code very good, they didn't receive very good results. But what was the reason? because but why, when the number of classes goes up, the accuracy goes down? Why? What is the reason? The reason is because, okay, there is misclassification here because we have data comes from healthy people, like just open eyes and closed eyes, but the rest of characteristics is the same. So there is a misclassification here, and then the accuracy will be go down, but except these two methods, which the result is obviously is better, like a Greg and RI. So next step, they consider different classifiers, like a tree classifier over time frequency distribution, and calculate their accuracy with this formula. And some parameters calculated, like maximum, minimum, as well as average and standard deviation. And again, you can see very good results for the two first classifier, but not for the first, but still better than the rest of them. Well, here you can see different classifiers which apply to this data set comes from EEG. For KNN with K equal 5, and for decision tree with C 4.5. And for ANN, you can see very good results in compare of the rest of the classifiers. So in this paper, they applied, they received the data set and then extracted features from that data set. And this, they wanted to say that in the previous work, they didn't consider a reflection of time, a reflection of the energy distribution over time frequency plan. But here they consider it, and they could receive a very good result. And they wanted to show that for different time frequency feature extraction, and then for different classifiers, it's so important to consider which classifier applied to which time frequency distribution. Well, yeah, that's it. You.
Thank you very much. Timing is perfect. So I asked the PhD students to give a